this lecture, we will talk about solution to a linear time varying system. And in order to obtain the general method for the construction, let's begin with considering the simplest case. So this is the simplest possible case that belongs to this problem. So we're considering first order system, homogeneous, meaning that we have no input, the input term is 0. Our state is R, it's just a scalar, and we consider a case where our A matrix, which is scalar, because we consider the first order case, is constant. Therefore, the system becomes LTI. Note that in certain contexts, LTV, linear time varying, may mean not LTI, not linear time varying. But in our context, LTV means not necessarily linear timing varying. Okay, so this LTV is the general case, or it's a generalization of the case LTI. In other words, an LTI system is also an LTV system, but not vice versa. Okay, so this is the simplest first order differential equation. X that equals alpha times x. X is a scalar, alpha is a real constant, and suppose that we start from some initial condition on the real line. Let's call it x0. Okay, so x0 is 0. Okay. Now, the solution to this case is straightforward. We know that is x of t. Okay. Solution to this differential equation starting from this initial condition is e to the alpha t minus t0 times the initial condition x0. Okay. Now, let us consider this as something, a function of time, that's multiplying the initial condition. And that's something, let's give it an n. Let phi t0 be defined as this function. Okay, the exponential function. We call it e to the alpha t minus t0. Then, with this new notation, we can write the solution as x of t equals that function phi, time, which is a function of t and t0, times x0, where x0 indicates the initial condition, initial time being t0. Okay. So we can write x of t equals phi t0 times x of t0. Okay. Now, let's make two very important observations regarding this very simple case. They are very important observations because they will give us ideas on how to generalize the solution or the approach for the LTV case. Okay, where this is where the state is a vector in Rn, and our A matrix is possibly time varying. Okay. Now, the observations that we make, and which will play a key role in our generalization, are the following. First of all, phi of t0, t0. So if for this function, if you plug in t equals t0, that is, if both arguments of this function are equal, then we have t0 minus t0, 0, and regardless of alpha, we have e to the 0, which is 1. Okay, so this equals 1 for all alphas. Okay, and because of this property, we have x of t0 equals 1 times x0, that is x of t0 equals x0, which is the initial condition constraint. So this property gives us directly the initial condition constraint. X at t0 equals initial state x0. So this is the initial condition constraint. Not that there is another constraint that should be satisfied by our solution candidate, and that's clearly the initial condition constraint. Okay? And it turns out that in order for this differential equation constraint to satisfy, this has to satisfy another property, and that property is not good to see. If you differentiate phi with respect to the first argument or with respect to t, then what you have is your A matrix, in this case just an alpha, times that function itself, phi. T minus t0. Okay, so if you write this as phi dot, well, so what we have is phi dot equals alpha times phi. In other words, this object that we defined must satisfy the initial condition, execute the differential equation, and from that follows that the solution defined as phi times initial condition satisfies the differential equation. So this property immediately gives us x that equals alpha times x. Okay? In other words, thanks to this property, the differential equation constraint is satisfied. Okay, now by focusing on these properties, let's consider the general case. By general, we mean the state belongs to Rn, okay, and the A matrix is now trinary, n by n trinary matrix. Okay, now consider x dot equals at times x. At is an n by n matrix, possibly with trinary entries. At belongs to Rn by n for each time t. And x at t0 equals, this time, a vector, not a scalar. And that vector, because A matrix is n by n, that vector must belong to space Rn. And now the question is, what's the solution for this trinary differential equation? X of t. Okay. Now, we start with a guess. And our guess will depend, it will not be an arbitrary guess. Our guess will be motivated by these very simple but key properties satisfied by this function phi that we defined in the simplest case. Okay. So suppose there exists a matrix calling capital phi, which is a function of two real variables called t and t0. Okay. And for each pair of t, t0, it's a matrix in Rn by n, satisfying properties. Okay. And by these properties, or those properties, will be coming from the simple properties for satisfied by the LTI scalar case. Now, this property will be transferred to the general case, not surprisingly, in the following form. If both arguments are equal, in the scalar case, we have this function equals 1, and now that 1 will be replaced by the identity matrix, okay, of dimension and size. So this includes identity matrix, n by n identity matrix. Let's call this property 1. And the other property will be a generalization of this simple property satisfied by phi. That is, the function phi satisfies the differential equation. In other words, d over dt phi t0. So we are differentiating with respect to the first argument, equals alpha here, and now instead of alpha we have the general a of t times phi itself. Let's call this property. Okay. Now, if somehow such an object exists for a given differential equation, x equals a of t times x, it's very easy, okay, it's almost immediate, that solution constructed as x of t equals phi t t0 times initial condition vector immediately satisfies both differential equation constraint and initial condition constraint. Okay. Then the solution constructed as this matrix phi t t0 multiplying initial condition vector. Okay, this is a vector in Rn, this is an n by n matrix, this is also a vector in Rn, n by n matrix times the vector in Rn gives us the vector in Rn, and that vector is the solution. That will be the solution. It's very easy to see why this will be the solution. In order for a candidate to be the solution, it should satisfy two constraints, initial condition constraint. Let's see if it satisfies. Plug in t equals t0, this matrix becomes identity. Then what we have is identity times x0, which is x0. Therefore, the initial condition constraint is satisfied. As for the differential equation, take derivatives with respect to time of both sides. Okay? Since it's a constant vector, the initial condition vector, and taking derivative with respect to t, what we have is partial derivative for phi with respect to t, and which is a of t times phi t t0. Okay? So here we have x dot, and here we have a of t times phi times x0, and phi times x0 is x of t, so what we have is x dot equals a of t times x. So it's very easy if these properties are satisfied that this x of t equals phi times x0 is the solution. Okay, now let's consider this very important matrix. Okay? How that matrix can be constructed. Let's think about that a little bit. How to obtain phi t t0, this n by n matrix satisfying two properties. Okay, is the question we will address now. Okay. For the construction, we will look at the only thing that we have in our hands, which are those two properties, property 1 and property 2. So we have this differential equation to be satisfied by our candidate phi. Let's integrate both sides. Okay, so equation 2. Let's integrate equation 2 from t0 to t. Okay. That yields phi t t0 minus phi t0 t0, whatever phi is. Okay. So this is the integral of the left-hand side. As for the integral of the right-hand side, what we have is from t0 to t, a S1 phi S1 T0 ds1. So S1 is our then dummy variable of integration. So wherever we see T here, we plug in S1 and integrate with respect to S1. And yet the borders of integration is from T0. Okay, now again, this time we use the property 1, that is, if both arguments are equal, and this matrix has to be identity. Therefore, this is identity. We take that identity to the other side using property 1, and we can write phi T0 equals identity, this from to the other side, plus that integral T0 to T A S1 phi S1 T0 S1. Okay. Note that this is not really a way, this is not an explicit expression for phi T0, because here we have phi T0, but on the right hand side we also have phi, that same function. Okay, so it's a circular definition. So let's therefore go one step further. And by going one step further, what I mean is we have an expression for phi T0. So let's replace this phi with that expression. So let's call this 3. Then from 3, or rewriting 3, we have phi T0 equals identity plus T0 to T A S1. And now, instead of this phi here, we use this phi. Okay, what I mean is the following: I plus T0 S1 A S2 phi S2 T0 ds2. Okay. So we replace this phi S1 T0 with this integral using the very equation 3, and we just have S1. Okay. Again, we have something more complicated, and we're not able to get rid of this phi dependence, but okay, that equals next plus T0 to TA S1 plus T0 to TA S1, and we have T0 to S1 A S2 phi S2 T0 ds2 ds1. So that's a little bit simplified version, but still we have phi term on the right hand side. So if you keep doing this, so each time there appears a phi, you replace it with this expression here, which itself contains a phi on the right hand side. You increase the number of terms in your construction. Phi T0 equals identity plus T0 to TA S1 ds1 plus T0 to TA S1 T0 to S1A S2 ds2 ds1 plus a term that contains integral of AS1, then integral of AS2, then integral of AS3, and so on. So you keep adding more and more terms. In a sense, what you're doing is you're pushing this phi further and further toward infinity. Okay, and then you obtain this construction which contains infinitely many terms. Okay, and this series, after its inventors, are called Peano-Baker series. Now, it turns out that under very mild conditions on the matrix A of T, this series always converges. Okay, and that yields the following very important theorem. The unique solution to x equals a of t x, x t0 equals x0 is x of t equals phi t t0 x0, where matrix phi is constructed through Piano-Baker series. Okay, or you don't use this method to construct it. There may be other methods, but so in that case, you can take this as the definition of that matrix phi is constructed. Or defined, if you don't like this word, through the Piano-Baker series. The matrix function phi t0 is equal. Therefore, it has been given a name. It's called state transition matrix. Now let's emphasize certain properties of that phi. Those properties directly follow from the definition. Some are easily, some are a little bit in a more difficult way. So, properties of state transition matrix. P1. Here work dt phi t t0 equals at phi t t0. So it satisfies the differential equation. Okay, so it was atx. But there's an important difference. Here x is a vector, whereas in this differential equation, our variable is an n matrix. And phi t0 t0. Whenever the arguments are the same, this matrix, regardless of a of t, boils down to the identity matrix. This property is, or these properties are the properties from which we obtain the Piano-Baker series. Okay, so that's in a sense a tautology of that problem. Phi satisfies this problem. Now there's another important property. Phi ts times phi s tau. So ts and tau, there are three real numbers. Equals phi, so we want it determined 3s t tau. And this is called semi-group property for all ts. Semi-group property. And another property which will be useful in analysis is phi ts is always invertible for all t s and a of t, and its inverse equals phi of st. So what you do is you use that the variables ts becomes st. ST bar. Okay? And this follows from simply T2. Okay? So what we do is plug in tau equals T. So what we have is phi Ts times phi St equals phi T T. Phi T T is identity matrix. Therefore, phi Ts times phi St equals identity matrix, which means these two matrices must be the inverses of one another. Now let's go one step further and generalize theorem 1 to the non-homogeneous case. That is when we also have an input, an answer input in the picture. Theorem 2. The solution to the non-homogeneous case, that is x that equals at x plus b t u x t0 equals x0 is obtained using the state transition matrix as follows: x of t equals phi t t0 times x0. So this is the solution when u, either the input or b matrix, is 0. But when this term is present, we also have to have another term in the solution, and that term is this integral from t0 to t. Phi t tau b tau u tau e tau. Okay, so that's the solution. Here is a demonstration of this claim. Let's go with that. In order for this to be a solution, it should satisfy two constraints: initial condition constraint and differential equation constraint. Let's start from the easy one. There's the initial condition constraint. Initial condition constraint is xt0, okay, must equal x0. So let's see whether it indeed equals to x0. So for this, plug in t equals t0, where we use t. So what we have here is phi t0 times x0 plus t0 to t0. Then we have this integration. This equals what? Now, since the integration is from t0 to t0, this is 0. And since here we have the transition matrix with both its arguments equal to one another, this is identity matrix. Okay. So what we have that was xt0 equals identity times x0 plus 0, which is x. Hence, the initial constraint is easily satisfied. As for the differential equation constraint, what we have to do is we have to take this candidate and compute its time derivative. So x dot is, by definition, x dot is differentiation with respect to t. So let's differentiate with respect to t. What we have is d over dt, this is our x of t, phi t t0 x0 plus the derivative of this integral t0 to t. And we have the integral. Note that we cannot compute this integral. We cannot just simply take the integrand and plug in t wherever we see tau, because the integrand itself depends on t. So it will be composed of two terms. And what we have is the following. First of all, this is a constant vector. Therefore, to compute this derivative, all we have to look at is this a over dt of phi. And that, from the property P1, we have a of t times phi. Okay, so what we have here is a of t times phi t t0 times x0. So that's that derivative easily computed. Then what we have is plus t0 to t partial derivative with respect to t of the integrand phi t tau e tau u tau e tau. Then what we do is we take the integrand and plug in t, okay? Because t0 is also to be constant. Then what we have is phi of wherever you see tau, you plug in t, t, et, and ut. Okay. This equals what? A of t phi t t0 x0 plus. Now, partial derivative of phi with respect to the first argument is a times t times phi. So what we have here is therefore a of t times phi t tau and multiplied by the rest. A of, since integration is with respect to tau, you can take this a of t outside the integration. So we have t0 to t phi t tau e tau tau tau, and then phi t when both arguments are equal, it is silent as the matrix, therefore this disappears, and we have plus et ut. Then a of t. Now that a of t multiplies this and that. Phi t t0 x0 plus t0 to t phi t tau e tau u tau e tau, okay, plus et ut. Okay. And since this is no other than x of t, we have x dot equals a of t times x plus e of t times u. This here is x of t. Therefore, the differential equation constraint is also satisfied. This is a simple demonstration of the claim that's made in this second figure. Okay, now let's quickly apply some of our findings to some simple exercises to gain some familiarity with our new object state transition methods. This is our first exercise. Okay. For which I'll not provide a solution, but just part of the solution. And there will be some steps, and those steps that will be skipped is for you to fill in. Okay, so we're considering the following second order case: 0, 0, t, 0. This is our time varying A matrix. But it's a very simple A matrix because most of its entries are 0. X plus, this is our time varying B matrix. 0, t squared times. Okay. Let the initial condition be arbitrary. So let's call them x1, 0 and x2, 0. And the output for this second order system is defined as a second state variable times x. Therefore, our C matrix is constant, 0, 1 times x. And about the input input is also a constant sigma. Okay, its value is 1 for all times t. The question is, what's y of t of this system? Okay, here is part of the solution. Since it's not the entire solution, I'm calling it the answer. So let's compute the state transition matrix. Phi theta equals identity plus, so we're using the Piano-Baker series, so what we have to do is we have to add infinitely many terms. But since we now have a very special A matrix, it turns out that the Piano-Baker series contains only 2 terms. All the terms starting from the third term, dash tau ta s1 s1. Okay, and then we have plus integral of as1 times integral of as2 as2 ds2 and so on, and then we have as1 integral as2 integral as3 and so on. But since A is triangular matrix with diagonal entry is 0, as1 times as2 is 0. Okay, and that would mean that all the higher order terms are 0. In other words, this is our Piano-Baker series for this matrix. And it's very easy to compute this integration. It turns out to equal 1 square minus delta square. Zero, zero, zero. So this is the result, the result of this integration. And to that, what we're doing, we're adding the identity matrix. So that means these entries here would be 1. 1 here, 1 here. That's our state transition matrix. Once we have state transition matrix, we can, using our theorem 2, we can write down the solution x of t equals phi t t0, and in this case t0 is initial time is 0. So what we have here is t0 times x0 plus from 0 to t phi t tau b tau u tau. Okay, and u tau is 1 split, and then u phi of t tau is here, plug it here, multiply with b, and since b chooses the second column, the second column is very simple for the state transition matrix. It's not difficult to compute that. You check all that out, and the result is this x10 and x20 plus t squared over 2 x10 plus 1/3 t cubed. Okay, so that's x of t. And finally, what we're asked for is y of t. Y of t is the second state variable, x2 of t, and that means we're talking about this entry as y of t equals x20 plus t squared over 2 x10 plus 1/3 t cubed. Now, before we finish, let's talk about another exercise. Briefly. Given the system matrix of the LTV system, A of t equals 0 t 0 to find phi let's obtain the state transition matrix. Okay, for this given A of t matrix. One way is the Gannon-Baker series, summing up infinite in many terms, but let's approach the problem from another angle. That angle has to do with the fact that this A of t matrix is, although not simple as this one, it's still quite simple because many of its entries, half of its entries are zero. Okay, here is answer, okay, which means the solution where certain steps are omitted. X dot equals A of t times x. Okay, so this is where A of t appears. X is a vector in R2. This is a 2x2 matrix. Now let's write this vector differential equation as two scalar differential equations. So what we have is x1 dot equals 0 times x1 plus t times x2. And x2 dot equals 0 times x1 plus 2 times x2. Now let's consider the second equation. First, it's an LTI scalar equation. We can immediately write the solution for x2 of t. Let's do that. x2 of t equals e to the 2t minus tau x2 initial. Okay, where tau indicates initial time. Okay, that was easy. Let's call this equation. How about x1 that equals tx2 equation? Let's also talk about that. x1 dot equals t times x2. Now x2 is known explicitly, which is e to the 2 times t minus tau times x2 tau. That can be written as t e to the 2t, then e to the minus 2 tau x2 tau. Okay. This is simply the first equation where x2 is replaced by that expression. Then integrating both sides from t to tau, what we have here is x1 t minus x1 tau. This is our left hand side, and then the integral of this term from t to tau is e to the minus 2 tau x2 tau. Okay. This term can be considered as constant because we're doing integration with t. And then times tau t s e to the 2s ds. Okay. So this term gives rise to that integral. And then using this definite integral formula for e to the 2s, we can write x1 of t equals x1 of tau, where this guy is thrown to the other side, and then we can compute this integral easily. The answer is t minus 2 minus 1 over 4 e to the 2t minus tau minus tau 2 minus 1 over 4 times x2 times tau. Okay, let's call this equation 2. Now at this point we have both x2 of t and x1 of t explicitly in terms of the initial conditions. By initial conditions we mean x2 of tau and x1 of tau. We're treating tau as our initial time. And by combining those two explicit expressions given in equation 1 and equation 2, we will now easily obtain the state transition matrix because we know that the solution is unique. So combine equations 1 and 2 and obtain the matrix form x1 of t equals x2 of t equals something times the initial condition vector x1 of tau, x2 of tau. And this something, a 2x2 matrix, should be our state transition matrix. Now let's figure out that something. For the first row of that 2x2 matrix, we look at the second equation, x1 of t equation, okay? So x1 of t equals 1 times x1 of tau, 1 times x1 of tau, plus this chunk times x2 of tau. Therefore, this should go to this entry. So that we rewrite it. It will be a little messy. T over 2 minus 1 over 4 e to d 2t minus tau minus tau over 2 minus 1 over. Okay, this entry for this function used here. How about the second row? For the second row, we look at the first equation, x2 of t equation. x2 of t equals 0 times x1 of tau, so this entry must be 0, plus this times x2 of tau. Therefore, this we have e to the 2t minus tau. Now what we have is x of t equals a matrix times x of tau. Since we didn't make any assumptions on t and tau are arbitrary, and since the solution is unique, this matrix here must be a state transition matrix. Okay, this is x of t. This is x of tau, and this matrix has to be a state transition matrix. Here's a nice exercise to finish the lecture with. Check whether this equation or this solution, this expression for a solution, satisfies the two constraints that it should satisfy, namely phi t tau equals a of t phi t tau, which will immediately give the differential equation constraint for x of t, and also check better phi of t equals identity matrix. Well, checking this is straightforward. Plug in t equals tau, then this becomes 0, this becomes 1, and what we have is identity matrix. Checking this requires just a little bit